linear system of equations, three things can happen. One of those things is that you get one solution. That's our favorite one because it makes us feel like we've done something, we've accomplished something by getting one solution to a system of equations. That means an answer for x and y. Okay, we got an answer for that. That is really our best case scenario. That's the scenario we want to happen for the most of our problems that we encounter, okay? Well, option number two comes up every now and then, and that's when there are no solutions. Okay, no solutions means you can't work. It doesn't work this way, okay? That would be, anybody ever heard the expression, you can't get there from here? I mean, you ask somebody how to get to somebody's house, you can't get there from here. You got to go here first and then go, okay? So no solutions means you can't find a place where these two equations match up. Okay, that's the other scenario, and that happens sometimes. Again, one solution is going to happen most of the time. No solutions happen sometimes, but sometimes you get this thing called infinitely many solutions. And that means there's so many answers I can't count them. Okay? You can't mess this one up. It has tons of answers. And we get infinitely many solutions. All right, so we're going to look at graphs and what that looks like on a graph and what we can do to kind of shorten our workload a little bit when these two special cases happen. Again, one solution happens most of the time. It's what we like to happen. It really makes sense when it does. It's the other two that are kind of special. And there are some shortcuts to recognizing these other two, where there maybe are not shortcuts on the first one. Okay? So some mathy words that go with that. So we go a little vocabulary here. If it has one solution, that system is called consistent. Consistent, it's always there. It's good. If you've got people in your life that are consistent, that means they're steady. They always got my dad is a good one. He's consistent. I can go to him and get advice. He's always got an answer. A good answer, usually. Okay? No solutions. Those are the people you probably don't want to go to because they're inconsistent. Okay? A no solution system is also called inconsistent. I'm going to use the one solution, no solution, infinitely many most of the time when I talk. But understand, these words, if you see them somewhere in this book or something, that's what they mean. They mean consistent, oh, that's one solution. Inconsistent, and that means no solutions. And then infinitely many solutions, well, it's got answers, so it's consistent, but it's dependent. So, and dependent. Okay? It's got answers, but it's dependent on what's going on. Well, it depends on what's going on, what kind of answers they are. Okay, it's got an answer, but it's dependent. Okay, consistent and dependent. Another word here that goes with this one would be independent. Now that will kind of tie it really together. Consistent and independent means you got one solution. Consistent and dependent means you got infinitely many. Okay. All right, so let's look at just a quick sketch of what that looks like as far as the coordinate plane goes. Okay, what's that look like when you graph these? Because this whole section is about graphing. Okay, so when there's one solution, I'm just going to sketch a graph here. I'm not even going to get equations for my lines. I'm just going to draw a quick coordinate plane. Or three of them. And one solution, you got two lines. And they cross. How many places is the red line touching the blue line? One. That's that one solution. Okay? One solution. That ordered pair right there for that point. For this one, looks like on my graph it'd be the point 1, 2 is about where it's at. Okay, 1, 2 is an ordered pair. Okay, no solution How many times do you think the lines cross? None, right? They never do. What kind of lines never cross? Parallel. What do we know about parallel lines? Their slope is the same. Very good. That's a great answer. The slope's the same. They have to be for them to be parallel. Okay, so no solution means they never cross. Those two lines are parallel to one another. Okay? Infinitely many how many times do you think they cross? Many, more than you count, right? So if I drew a line, I'll just draw this one with a negative slope just to be different. So there's the first line. And then I came back and I graphed the second line. It's going to be right on top of it. The line got a little bit off there. Let me redo. We see that red line is laying right smack dab on top of the blue one. It's touching it so many times you can't count them all. Okay, so that's an infinitely many situation. So we got one solution crossing in one spot. We get the ordered pair, we're good. That's it. No solution, they don't cross at all. We know those lines are called parallel. Joyner told us that the lines being parallel means they got the same slope. So that's going to be a clue to help us shorten our workload here. Okay? What do we know about these two lines? The blue and the red on the infinitely many. They got the same slope, and what else? Same coordinates. Everything's the same about them. So those two equations are exactly the same. Okay? If we get them in the form we need to in order to graph them. Okay, so let's look at some systems of equations and let's try to graph them and see if we can find a solution, if there is any. If there is a solution. All right, so example A. Here's our first system of equations. Let's say we had 3x plus 2y is equal to negative 4. And the second equation is x plus 3y is equal to 1. Okay, we got a system of equations, and I'm going to solve this by graphing. I know in Algebra 1 you guys learned some other methods. One of them was called substitution, another called elimination. We're going to get to that. We're going to do that. But we want to try to do this with graphing, and this is going to help us be better at graphing. Okay, I think this will help us even with our piecewise functions and things. We kind of struggle with some of the graphing lines there. What form do we want to put the equations in if we're going to graph them? Good. Everybody knew that. Slope-intercept form. What is slope-intercept form? Yeah, that's something you're so familiar with. You've been doing that for years. Y equals mx plus b. Okay, what's the m? Slope. The b? The y-intercept. Okay, so that's what we want to do. We want to get y by itself in both of these equations. So this is the good old algebra part of this. Is get y by itself. So this first equation, I'm going to subtract 3x and get 2y is equal to negative 3x minus 4. And then what do I do to get y by itself? Divide by that 2. And everybody gets divided by 2. And that gets us the equation y equals negative 3 over 2x minus 2. Okay, so that's our first equation. The second equation, maybe it's a little bit easier to do. What's the first move to get the second equation in slope-intercept form? Good job. Subtract that x, it's gone. That gets us 3y is equal to negative x plus 1. And then what? Yeah, divide everybody by 3. Man, there's a fraction in there. Golly, I don't like that. That's okay. We still got it in slope-intercept form. Not 1/2, but 1/3. Okay, so our slope's negative 1/3, and our y-intercept's positive 1/3. We just got to be careful when we go to graph this and how that works. Okay, so we've got two equations. These are the two we're going to graph. Okay, I'm boxing those in. So I'm going to go to a coordinate plane, and I'm going to graph those two. So draw yourself a little coordinate plane, and let's graph them Again, we're going to do this by hand, and I'm going to show you, you can do this with a calculator as well. But we're going to do it by hand first because it's hard to turn in a calculator. All right. Now, I'm going to graph that green one first because it doesn't have the fraction in there to deal with. So it's easier. Okay, it gets the rust knocked off first. What's the very first point I should plot when I graph y equals negative 3 over 2x minus 2? 0, negative 2. Be careful on your signs. That's a minus 2. So my y-intercept's at negative 2. So 0, negative 2. And then my slope is negative 3 over 2. So how do I count that? Good job. Down 3 and over 2. I could go down 3 and over 2 again if I wanted to. I could even go up 3 and left 2. And that's still a negative slope. Okay? So I'm just drawing that line. Try to be as precise as you can be here. It's one of the big things with this. I had a teacher in high school here. I don't know if anybody knows Mr. G. Allen Bruce. He was the math teacher here for 100 years or so. And he would always say, just get close. And then when you just got close and really weren't precise, he counted wrong. So be really precise. Try to be as accurate as you can with your lines. So count that slope as many times as you can. Does anybody need a straight edge? I got some y'all can borrow. Y'all are welcome to. Here, I'll just start passing them around there. If you need one, grab one. We'll put a box up here and you just drop it in that box that's here every day when you get it, okay? All right, now let's graph that red one. This was a little tougher because it's got the y-intercept where? A third of the way up. So that's a little harder to do, and you've got to kind of get a little smart about our guesstimation. So a third of the way up, it's a little less than half, so it's about right there. Okay? So you see that point, 1/3. And then my slope is what? Up over which way? Left. Okay, so if I go up 1, left 3, that gets me the negative 1/3. And that's going to put me in the correct direction to run into the green line, right? That's what I want to happen because I know these two are going to cross each other because the slopes are not the same. Slopes are not the same, you know they'll have one solution. The slopes are the same, we know they're parallel, they'll have no solution, so we wouldn't really even need to graph those.
If it's one, do we need to put like halfway between them?
Not quite halfway, but how much of a way? A third of the way, yeah. So be up 1/3, left 3. Up to 1 1/3, and then left 3. So about right there. We went down 1 over 3. Be about right there. And then we draw that line. So we're trying to be as precise as we can. A real sharp pencil helps with that. Unfortunately, my electronic pencil can't be sharp. So. There we go. That's pretty close. I'm going to be a little better. Go ahead, Jordan. Why didn't we go which way? We need to know that, okay? How many solutions is this one going to have?
It's going to have one.
One. Because they cross. If they cross, you know they're going to have one. The only way that they've got no solution is if the slopes are the same and the y-intercepts are different. The only way they have infinitely many solutions is if both equations are what? Exactly the same.
So what's the thing? Like
All right, so what is that ordered pair right there?
1 1/3.
It looks like -2 and then +1. That would be my x and my y value for that particular system. Graphing is not exactly the best way to solve systems, but it is a good way to get us started in solving systems and us learning, getting better at graphing, knocking that rust off of our algebra skills, getting y by itself and all that stuff. So really good lessons here to start with, okay? So to check that, you could take the x and the y and plug it back into the original problems and see if it works. -2 times 3 is -6. Plus 2 is -4. It works in the first equation. Let's try it in the second one. -2 plus 3 is +1. It works in the second equation. So we get the ordered pairs there. We can check them by plugging them back in as x and y. Okay, does that make sense? All right. Let's do another one. Let's say we had 8x minus y is equal to 0, or no, not 0, that's an 8. Equal to 8. That's a little better. And then the second equation is 3x plus 2y is equal to negative 16. That's a really good one. Okay, so what do we want to do with each of these? Slope-intercept form. Get y by itself. That's your first step. If you're going to solve by graphing, get y by itself. Get it in slope-intercept form. So first one, we'd subtract 8x. Get negative y is equal to negative 8x plus 8. And what happens to everything? Change signs. Yeah, divide by that negative 1. Get 8x minus 8. There's our first one we got to graph. I'm going to go ahead and work the second one, get it by, y by itself on it so that I'm just ready to graph once I get there. So subtract 3x. 2y is equal to negative 3x minus 16. Divide by 2. So there are my two equations. Are these going to intersect? They going to run into each other?
Yes.
Why?
They're parallel.
Are they parallel? No, they're not parallel. They happen to have what?
They get the same slope-intercept. No, they get the same one.
They got the same y-intercept. So what's that tell us about the solution?
That's what we need.
It's going to be the y-intercept because they got the same one.
Oh, yes.
How many places can two lines run into each other if the slopes are different? One. That's only one place that they can connect if they're different slopes. Okay? Let's draw it on the graph so we can visualize that. I'm going to make, the y-intercept I know is at negative 8. So I'm just going to make sure my coordinate plane's got enough room down there in the negative y direction. So I'm going to make it look like that. And then graph them. So I'm going to graph that green one first. Go down to negative 8. 1, 2, 3, 4, 5, 6, 7, 8. Dot. Up 8 over 1. That's pretty easy. I can do that. There's my line. And then the second equation, it's got the same y-intercept. So we know that that's my point right there. And then I'm going down 3 over 2. And, I know where they're crossing at now. Redraw that line real quick just to be more precise. And what's that ordered pair? Well, I said it a while ago. 0, negative 8. That's the...
So are we going up 3 and to the left 2?
You can go up 3, left 2, and we end up right there. I went down 3, right 2. Okay, and that's still a negative slope. Okay, we had a negative 3 over 2 slope, so we can go up 3, left 2. That still makes it negative. Remember, negative slope lines fall down and to the right. Positive slope lines, like this one has positive 8, this slope goes up and to the right. So that'll help you make sure you're putting the right direction on your lines there. Okay, so we're finding that place where these lines cross is what we're looking for. Okay. Let's try this one. 5x minus 2y equals negative 10. And I'm just going to write the second one out to the side here. 2x minus 4y equals 12. Since we know we're doing it by graphing, I'll go ahead and write it like that. Two different equations. We want to solve that by graphing. Okay, see if you can do that on your own. get started on your own. Re-record. So get y by itself. Boring, basic, same thing we've been doing. This one's nice. I like the first one. Y equals negative 2x plus 4. Hey, I got y by itself. Yay. Second one. Not much more difficult. Just one extra step. Divide by 2. And I get y is equal to negative 2x plus this fraction 3 over 2. What do I know about these two lines? They got the same slope. What's that mean about them? Parallel. And we know that because it's the same slope. Do we even need to graph these? No, because we know what about them? They're parallel, so they'll never what? There'll be no solution. They're not going to cross, so it's no solution. You can write the words no solution. There's a little symbol that means no solution that you can use. It's a circle with the slash through it. The empty set is what that means. Yeah, that's shortcuts. Remember shortcuts. All right, so no solution or the circle with the slash through it means no answers. Okay. So there. What else is that system called? What's the math word for that? Inconsistent. Yeah, inconsistent. If it's no solution, it's called inconsistent. So if you see that word, you know what's going on. All right, let's look at example E. And hang with me. We're getting close to the end here. Some time for you to work. All right, so let's say we had 3x minus 2y is equal to 10. And then 6x minus 4y is equal to 20. And again, I stacked them up because that's the way they're going to give them to you. But when I write it down to do my work, I'm going to write them side by side like that. What do I need to do? Yeah, get them in slope-intercept form. That's if you're solving by graphing this whole section. That's what you want to do. Get y by itself. Get it in slope-intercept form. So subtract 3x and then divide by negative 2. 3 over 2 x minus 5. Okay, there's one of them. Let's get the second one. All right. Divide by negative 4. Negative 6 over 4 reduces to be 3 over 2. Infinitely many solutions, and there's not a infinitely many solutions, consistent and dependent on this because it's the exact same line. What one line does depends on what the other one does. Kylie.
Can I put the infinity sign or many?
No.
I don't know how to spell
Infinite. I-N-F-I-N-I.
Just
T.
get close.
No. Spell it right. Spell it right. You guys can learn how to spell. I know. Autocorrect has ruined all of us. It's ruined. It has me too. So, important words you use in everyday life, like infinity, you need to know how to spell. You do now. You're in Algebra 2 class. You're going to use it some. All right. So, there we have infinitely many solutions. That's also called consistent and dependent. Remember, Consistent means it's got answers. Independent, one answer. Dependent, many answers. Okay. I will let you do this. IMS. We can do that for abbreviation. Is that cool enough? All right. That'll save you, a whole 10 seconds of life writing infinitely many solutions. So, all right. So this is what I need you to do. We're doing on our assignment for today is on page 156. We're working numbers 3 through 14, and then 17 through 28. Keep in mind, the ones that have no solution and infinitely many, you don't even have to graph. Okay, so you're only graphing the ones that have one solution. So that's gonna, it's gonna be the majority of them, but we also want to just, get that practice seeing that for the other. Let's throw a couple of word problems in there. Exactly.
This will be our homework.
And this will be what you're working on for the next 37 minutes, and if you don't finish it, homework. Okay?
We'll do all this today and do a lot and take Friday off. What do you think?
I didn't know how to do the big bus functions, so can I work on those two for handout?
As long as I get them by, get them tomorrow, I'll be fine. Yeah, that'll be fine.
Tomorrow, the 3 days?
Yeah, I'll take them to